And hello, everyone. Thank you for staying. Last talk of Google I/O 2014. It's been a long road, but we are almost done. Predicting the future with the Google Cloud Platform. That's what we want to do today, what we want to show you. The first question is why? Why now? And it turns out that we never had so much data in the world. It's really impressive how much data we can collect. Just going to I/O last year, we had this presentation, all the chips in the world, where we showed you how you were able to just map and visualize and collect all this data of all the chips, how they are moving around the world. Like a month ago, we released this data set with Professor Caleb Litaru, GDELT, over 250 million events all around the world for the last 30 years, detailing everything important that is happening around the world. But we can not only look at things at the world level, we can zoom in into particular regions, let's say South America, or particular countries like Brazil. Something important might be happening there. Let's zoom in further. Let's go to any city, Fortaleza, for example. Just to show you examples of cities, recently our friend Eric demoed how to stream all the power meters inside a city up to BigQuery with 50,000 rows per second. But let's zoom in into a particular place today. Let's go to this stadium. And as we can travel to the past with Street View, we can see how this stadium was being constructed. We have all this data. We are collecting everything that is happening. But the question today is, can we use this data to predict what is going to happen inside this place during the 90 minutes of a match? Well, your presenters. I'm today here with Jordan Tigani. He's one of the founder members of the BigQuery team. He also wrote the book on BigQuery. If you stay and you are good to him, he will give you a copy and sign it too. And I'm Felipe Hoffa. I work at Google Developer Relations. My job here is to do exactly this, to bring you the Google technologies that you can use and show you what you can do, so you can put them for your own use. So let's go to our topic today, predictions. We have been doing this for a long time, thousands of years. People have used crystal balls. More recently, for the last World Cup, this octopus did pretty well. He got like 11 of 13 matches right. We are not sure why or how. It seems he really liked the Germany flag, but we don't know. We can't ask him anymore. But we're going to use data, and that's what we have. When you want data, the first place you go to search for it, for me, it's Google. And some of the interesting data sets I got were, for example, the Wikipedia. Wikipedia has a lot of knowledge, but then it's hard to put this data into learning algorithms. But fortunately, we have Freebase. Freebase is a Google project that encodes a lot of this knowledge as facts in a SQL, in a table, in an RDF table. And we can use these facts. There are like 1 million facts there of the World Cup, players, teams. I also found this other open data set that people are building on GitHub with all the information from soccer matches, from history, from around the world, from the World Cups. So I got that, I got Freebase. I was able to use this data, for example, to find correlations like, do countries with a bigger population, do they do better at the World Cup or not? Ask me later about that because I really want to go to the next topic. That's Opta. This is a pretty cool data set. It's not open, but they are really changing the way that soccer can be analyzed. For any given match, they are recording event by event, touch by touch, what is happening, who is holding the ball, where is he standing. People are able to analyze the full history of a player, the full history of a soccer match in a very cool way. Just to give you an example, with this query in BigQuery, we loaded around 2,000 matches, 1,500 rows of information for each match. And here I'm looking at a particular match, Spain versus Netherlands. I knew that there was a goal at a particular minute, 43. And I wanted to know more information about it. And what did I get? I got information like when did it happen, who was the player, where he was located at the moment that goal happened. And I get a lot of details too, like, yes, this was a header goal, where was the goalie standing, where did the ball exactly go in. And now I'm able to use this data. The question is, when I have this data, how can I use it to predict? And for that, we have Jordan, our machine learning expert. So please, Jordan.
Thanks very much, Felipe. So I'm going to talk a little bit about using machine learning to predict soccer games. But first, I want to talk about soccer is really hard to predict. There's a lot of randomness. The team that's better doesn't always win. A lot of times you see a team, they have the ball, they're shooting the whole game, the ball just ends up not going in, and the other team, they get the ball once and they go and score and win. No, yes, exactly, like Germany. This picture here is it's a reenactment of a famous goal, but just yesterday, the Argentina versus Nigeria game, there was a shot, the keeper saved it. It went off his glove, it hit the post, came back, hit him in the head, went off the post again, bounced out in front of the goal, and Leo Messi came and just blasted it in. But that's the kind of thing that no learning algorithm is going to be able to predict. Just to give an idea of how sort of the experts do, these are guys whose job it is to predict the future, and they sort of turn their eye to soccer. Nate Silver, the guy who predicted Obama's victory as well as lots of other things, of the 16 teams that he predicted would make it to the second round, only 8 are still around. Goldman Sachs had another prediction using some of the same techniques that we're using, and they're not doing so great. Only 36% of their first matches. This is not a competition. We're not trying to beat anybody. We're just trying to show how machine learning can be used and to sort of set to level set expectations. So O Jogo Bonito is Portuguese for the beautiful game. It was, I guess, first attributed to Pele, talking about soccer. Soccer is a really, really beautiful game, and magical things happen on the field, and players like Leo Messi can do incredible things with the ball. Machine learning can be magical as well. For example, Gmail, when it detects that all of your spam is spam, and you never see spam anymore. I mean, that can be pretty magical. Or when you visit a page in Portuguese on Chrome, and it offers and it recognizes that and offers to translate it. That's another application of machine learning. But what I want to get across today is that machine learning is not magic, and it's anybody can do it, and it's actually sort of more than like playing soccer at Messi's level. It's more like managing a team, that somebody can learn to do machine learning fairly easily. So I'm going to use sort of an extended metaphor about managing a team. So just sort of bear with me a little bit. But so the first thing you do, whether you're managing a team or you're doing machine learning, is you want to set a goal. If you're the manager of the Brazilian national team with 200 million soccer-mad fans and players, you're obviously going to want to win the World Cup. However, if you're the manager of Tuvalu, a tiny island in the Pacific, even though in theory you could qualify and win the World Cup, that may not be the thing may not be your goal. Obviously, you still want to win every game, but when you're playing Australia, you may not assume that you're going to win every game. Your goal may be just to beat Vanuatu, the neighboring island. Similarly, with machine learning, you use the resources that you have to decide the prediction task that you're going to do. So we have this really huge data set and this really deep data set on club level soccer. So we have all the touches for 3 different professional leagues: the English Premier League, Spanish La Liga, and the U.S. Major League Soccer over a couple of years, and we can mine this data to build a model of how professional soccer works. However, that doesn't necessarily help us with the World Cup. And so we're going to have to try to stretch that a little bit in order to make our models work for the World Cup, because there just isn't the same depth of data available there. So once you have your data, once you have your goals, then you want to pick your team. And a manager of a team is going to want to pick based on certain attributes that they believe correlates with victory. They want fast people up front. They want people who can pass well in the midfield, and people who like to throw themselves on the ground as goalkeeper. In machine learning, the statistics that you use, you want to build statistics from your data that correlate well with whatever you're trying to predict. So for the soccer example, that may be whether the team takes a lot of shots, whether the team gets the ball in the other team's third of the field a lot, whether they pass well, whether they foul a lot. So you want to, sorry, just lost my train of thought. But after you've built your features, after you've computed those statistics, the next thing you want to do is train your team. And the nice thing is in machine learning, you use the same term as in soccer. You train a machine learning model, and that you train it to find patterns. And now that sounds a little bit mysterious. It's actually relatively straightforward. So we can show how this works in a somewhat simple example. So now this is data that we've gotten from our data sets about the probability of scoring a goal based on how far away from the goal the shot was taken. And to a human eye, you can see that there's a clear pattern here, but it's a little bit more difficult to get a computer to recognize this pattern. So one way to do that is to make the pattern simpler. And if we take the log of the distance, so rather than using the distance by itself, we have a much more simple pattern, and we can use a linear regression, which is a statistical tool that's present in spreadsheet packages and people may be familiar with, to essentially draw a line through that data. And people don't necessarily think of this as a prediction tool, but actually this lets us predict, given the distance the shot was taken, lets us predict the probability that that's going to go in for any distance. So the type of machine learning algorithm we're going to use here is not linear regression, but it's another type of regression, and we're just going to fit to a different type of curve. This is a logistic curve, and the nice things about it is it's bound between 0 and 1, which fits well for probabilities. The other thing is that it more easily captures nonlinear relationships between the data. So for this same example of distance from shot on target, we can fit a relatively good line to that data without having to translate it first. So I mentioned, fitting the line to the data. So we're going to keep track of a statistic, and it's called R-squared, and it's a measure of how close your line is to your data points. There's not necessarily a good rule of thumb for what constitutes a good one or a bad one, but you just want to make sure that, or it's a good way of comparing two subsequent models as you're iterating through different ideas. So when you're fitting data to a model, one thing you have to worry about is overfitting. So here's three soccer players who have won World Footballer of the Year in the last 15 years: Ronaldo, Ronaldinho, and Cristiano Ronaldo. You may be able to detect a pattern here in their names, and I can come up with a regular expression that can capture this. But you may not want to turn this into a predictive algorithm, or maybe you do. So I think I can predict who's going to be the next World Footballer of the Year. He's been under everyone's noses for the last 40 years. Ronald McDonald, the McDonald's mascot. Premier League scouts, you don't have to give me a finder's fee, but maybe some cheap tickets would be nice. No, but clearly this is absurd. It's a coincidence, and machine learning algorithms can be good at finding coincidences. And so the way you prevent that from happening is a technique called parsimony or Occam's razor. And you want to find the simplest possible explanation. And the way you do that in an algorithm is you penalize complexity. So if you try to come up with some really bizarre, complex model, that model will not score as highly as another one. Whether you're building a team or you're building models, you want to keep score. So usually when you train your data, you break it into two pieces. One piece is your training set, and the other piece is your test set. The training set is the data that you actually want to use to build the model. The test set, on the other hand, you keep to the side so that you can validate that model is not just regurgitating facts that it already knows, but can actually be used on things that it hasn't seen before. So a metric that we use to see how well we're doing is called lift. And that just tells how much better are we doing than random chance. Accuracy would be sort of maybe the obvious thing to use, but the problem about accuracy is that it doesn't reflect underlying probabilities. For example, soccer has 3 possible outcomes. So if you can guess 50% right 50% of the time, then you're actually doing pretty well. But if you're just looking at accuracy, 50% sounds like it's a coin flip. So lift actually lets us measure that more accurately. And so here's another more complicated way of looking at accuracy. And this is the receiver operator curve, which is kind of a strange term, but it comes from finding U-boats by radio detection in World War II, and the name stuck. But we have this dotted line going from the bottom left corner to the top right, and that's pure luck. So if you're right on that line, that means your model is terrible. So the further you get away from that line, the better. So I won't go into details about what this necessarily means, but we'll see it a little later when we're comparing models. The other thing about machine learning is it's an iterative process. You try it once, you keep trying, and it may not work. You need to sort of put more creativity into coming up with good features that are going to work for you. So then once you have your model, you've built the model, you've tested it, you've iterated on it. You want to do the thing that we're all here to do, which is we want to actually use it to predict. And so I'm going to switch to an IPython notebook. And so IPython is sort of the visualization of a suite of scientific tools for Python that lets you do lots of mathematical and scientific programming, and has some built-in machine learning algorithms as well. Okay, it worked. Okay, so you don't necessarily need to understand every line of this code. I'm just going to sort of go through. This is how it would work, and this is how you can do it. So this IPython notebook is connected on the back end to a Google Compute Engine instance. You can also connect it to a cluster of instances, and we did that for some of the more hardcore computation that we have done. It also is using pandas, which has a convenient BigQuery connector here. You can see that with essentially one line of code, you can run a BigQuery and turn it into a pandas data frame and operate it on it that way. And generally the first thing you want to do in machine learning is you want to kind of get a feel for your data. And so we'll just see how big our data is. We've got over 2,000 matches, 1,700 touches per match. And then as Felipe showed, we have multiple facts per touch. And there's about 13 million of those in our data set. Then we want to build our features, and our features are built by this actually very complicated BigQuery query. It's 11,000 characters long, 15 joins, and 8 group bys. So I won't show that here because it wouldn't necessarily be interesting. But with BigQuery, we can just send one giant query to BigQuery and let it worry about it, rather than having to sort of build a pipeline where we pull data down and operate it on it iteratively. So the next step is we run the query. We're gonna split out the World Cup data from the club data, because we want to build our model on just the club data. And so here's an example of what our features look like for actually, this is the Chile-Netherlands game. Sorry about that one, Felipe. Netherlands won Netherlands 2-0. but we have the pass rates in various parts of the field. We have how many goals were scored in previous games. And actually, the way we're doing this is we're taking, in order to predict what's going to happen in one particular game, we're taking an average of statistics that happened in the last 3 games, assuming that those will sort of hold in the next game. And if you're following the World Cup, you may notice that there's a reason for that 3 number, which is right now every team has played exactly 3 games. So we have 3 games that we can use to inform our models when we're looking at the World Cup. As I mentioned again, you kind of want to get a feel for your data. This is building crosstabs of goals to whether you win, tie, or lose. And so we can see here in the top left corner, if you don't score any goals, you're going to lose about 2/3 of the time. Whereas kind of towards the bottom right, we see that if you score more than 6 goals or more, you're more or less guaranteed to win. The nice thing about this particular crosstab helped us find a bug when we were debugging BigQuery, because in the World Cup or in tournaments, in the knockout stages, if the game ends in a tie, then it goes into penalty kicks. And so we end up seeing teams that scored 7 goals who lost, which sounds a little bit weird, but the reason was because in our data, those all showed as regular goals. And clearly we wanted to strip those out of our data when building the model. So kind of playing with the data a little bit can help you prevent bugs in your system. So next we want to train our model, and we're going to split out the test set here that we're going to use for validation. You can see the R² is about 12% on this one. The model training also lets us do feature selection, and it tells us which features turned out to be important for that model, which ones didn't. So we can see the features that correlated positively with wins were whether you're playing at home. Actually, home field advantage is a huge deal in soccer. Things like how well you passed in the opposing third of the field. There were some features that were dropped that just turned out to be not interesting at all by the Ackermann's razor principle. How many fouls your opponents had, or how many shots your opponents had in previous games. And there's also negative features, which are features that mean you're less likely to win. And so op passes is a little bit of a weird name, but it's how well the opponent's people passed against your opponent. Op expected goals is your opponents, how many shots they had, and how many goals you would have expected them to have, etc. So then we want to predict wins in club level data. So we run some quick predictions, and so here's some examples. So we predicted Manchester United would beat Wigan. That's probably not a surprise to anybody, and we got that one right. We predicted Manchester United would beat Tottenham Hotspur, which people would expect would happen, but actually Tottenham Hotspur upset Man United. But these are sort of anecdotes, and you want to be able to collect these into actual data. So we can validate this. We can compute the lift statistic. So we have the lift is 41%. So we're doing 41% better than random. And here's the ROC curve. And this one isn't necessarily that interesting until we show the next model. So one thing that if you're only looking at the last 3 games, the one problem is you may have had 3 really easy games, you may have had 3 really hard games. And so we want to be able to coordinate those together. And so what we do is we run another logistic regression that ends up stack ranking all of the games by sort of building a lattice among who's better than whom in terms of all the teams that have played. So we do that logistic regression, and we compute a power statistic. And if you've seen like the FIFA Coca-Cola power statistic for soccer, or college football has power rankings, that's essentially how that's created. And we're going to compute that power ranking. We're going to add that back to our model as one of our features. So when we compute the power statistic and add it back to the model, we can see that our lift goes from 41% to 55%, and our ROC curve, we can see it moves further away from that luck line in the middle. The new one is the blue line. Okay, so we've predicted club soccer. But we want to be able to predict the World Cup. I mean, that's what we're here for. So we basically have to apply some of the same techniques here. There's a lot of code here, but I wouldn't necessarily worry about it. And we can run the predictions, and here's our predictions. And before we go too far into that, I'm going to give it back to Felipe, and we'll talk more about those in a minute.
Let me take this. So let's go to halftime, if I can. Where's the here? Present. Awesome. So what do we have here? What did we learn? We know how we can predict. Use this data. We can use IPython, pandas to do a linear regression, a logarithmic regression. But do you want to know what are our actual predictions? For example, this Saturday, 9 a.m., Brazil is playing Chile. Who thinks that Brazil is going to win? Chile? Come on. Well, machine learning said that Brazil will win with a 72% chance. You were close. Colombia versus Uruguay?
I think they're both good teams, but now that Luis Suarez is out for biting, I think Colombia is probably going to do it.
Let's see what our machine learning said. 69%. Okay. Netherlands versus Mexico. Mexico.
My guess would be Netherlands, but having seen them play Spain, but Mexico's a good team too.
Computer says 55% Netherlands. We can call this too close to call, so we have to wait for this. Well done, Mexico. Costa Rica versus Greece.
That's a tough one. I'm gonna have to go with Greece.
Costa Rica 60%.
Oh.
France versus Nigeria.
I think that should be an easy one. France.
92%. That's a lot of confidence there. Argentina versus Switzerland.
Argentina looks hard to beat this World Cup.
68%. Germany versus Algeria.
Germany looks even better. Almost.
93%. Belgium versus Belgium. USA. 68%.
Oh.
We will see. Who will be the finalists? I don't know. We might try to guess. We think it's Brazil versus Argentina, and the prediction is 55%, so we can call it too close to call. Now, whoever is watching this video in the future might know what all happened, so please let me know in this video.
We can always change the video.
Yes, we can change the video. So yes. Not only we can change the video, we are not doing that, but things change minute by minute. We run our static predictions here, but sometimes you might have the best team, the best players, and things change in the first 5 minutes and you lose your best players. Or one of your players might bite too hard. And that changed the whole outcome of the game. And as you saw yesterday with Eric Schmidt at the keynote, the cool Eric Schmidt, we are able to stream all the data using data flow. We can get second by second what is happening. And the question here is, can we use that data, the facts that are changing during every second around the world, can we use it? Can we put them inside our prediction models? Jordan?
Okay, let's see what we can do. So you guys may have seen in the keynote, this is a screenshot from the demo app that we built. It's also been available in the sandbox, but this sort of shows minute by minute what we sort of expect to have. So we want to build a real-time model that'll let us know from inside the game who we think is going to win. The way we're going to do that is a Markov Monte Carlo simulation, and that may sound rather confusing, but essentially what it is just a video game that there's a player, he's got the ball somewhere in the field, and he has some options. And one option might be to pass, one option might be to shoot, one option might be to get fouled. And we compute conditional probabilities for each of these possible events, and then we traverse a state machine based on the conditional probabilities. And then we can iterate through that state machine to run an entire game. So we can see, okay, we run through that, and Team A won, and they scored 3 goals. So that doesn't necessarily tell you too much about what the probabilities are, but we can get probabilities by running this 10,000 times in parallel. And then each time Team A wins, we give Team A a point. Each time Team B wins, we give Team B a point. And then we can compute the probability of the outcome that way. And so this is sort of what the data flow pipeline looks like. Don't necessarily worry about what those boxes mean. But so we have this data that's coming in from Opta. That touch-by-touch data, we get that record by record, and we can sort of add that to our model. So what can we do? What can we do to incorporate that data into a machine learning model? So what we can do is we can use the data that's coming in to know exactly where we are in the game, exactly where we are in our Monte Carlo Markov chain model. Anyway, and we can run the game forward into the end, and then we can compute probabilities of Team A versus Team B winning from where we are in the current game. And so I can show a quick demo of this. This has been up at the sandbox for the last couple of days, so you may have seen Eric Schmidt run it, and can you just run that? So we're seeing basically this Monte Carlo running of an entire game, and then you can see histograms of who's going to win and who's not going to win. I think this is Brazil versus Croatia. I don't know. In the sandbox, we were showing Brazil versus Croatia. Can we switch back? We don't need to necessarily wait until this is done.
We're back.
And that's it.
So what did we learn? It's almost the end. Machine learning is like training your own team. Set a goal, pick your features, do the training, measure the lift, practice, predict. And after all is happening, try to understand. Look where you can find correlations. And the next step is finding causation. We might say that making predictions is hard, but it turns out it's very easy. We just made it. It's harder to be right, but it's even harder and more interesting to make them happen. Because as you understand the world, you can use this information, not only in soccer, not only to win the next match. You can use all the data you have to find patterns inside your city, how your city is moving, how the world is moving, where things are going, and how you can change it. And with this data, with these tools, you can go from divination to really having the world in your hands. Thank you very much. Use this, go change the world. Any questions? Thank you for staying. I know it's over, but we have 10 minutes for questions. Or less?
Yeah. The obvious question is, why didn't you use Google Prediction API, and why did you decide to build your own algorithm?
So one thing I want to say about the Google Prediction API is that the Google API Prediction, the underlying algorithms are awesome. It's actually the Google Prediction API uses the same technology as most of Google's machine learning. Then it's used throughout ads, throughout spam detection, throughout language detection. So it's not that the prediction API is not a toy. We didn't use it because we wanted to show how all the bells and whistles worked. So the prediction API kind of abstracts you away from some of the more funky or perhaps interesting parts of machine learning. So we wanted to sort of give a little bit of machine learning primer as we were going.
Understand the coefficient influence of each feature?
Yeah, well, and that's one thing that you don't get from the prediction API is sort of the feedback about feature selection.
Right. did you compare your coefficient versus what Google Prediction API did, and did you do a benchmark against these two things?
We haven't done that actually.
Okay, right. Thank you.
Sure.
My question is, what tools or maybe languages you use for fast prototyping? As I understand it is Python, but maybe something else. I mean, you don't use Google Prediction API for your own prototyping, yeah?
Python is used heavily at Google, so IPython is really nice to be able to predict. There's some things that are missing in Python, pandas, etc. But the nice thing about that is you can call into R as well. So R has vast libraries of scientific applications.
And second, personal question, I think. What kind of data sets do you like to learn? Each of them.
Yeah. So exactly, I don't exactly get the question. What data sets we like?
What kind of large data sets? I see football data sets. You try to learn, or maybe something else.
Yeah, look at GDELT. With GDELT you can see what is happening in the world right now. Last week someone uploaded all the taxi rides in New York from 2013, and just to be able to see every pattern, how people are moving, there are vast areas to discover there. I also love looking at the Wikipedia logs. DNA, you can go into genetics also with BigQuery. There are a lot of impressive things you can do.
And you?
Anything I can get my hands on. Soccer is a passion of mine, and so I was really excited to be able to get the data to be able to do this.
Okay, thank you.
Sure.
You get a book.
You get a book. You get a book.
My question is, what visualization library did you use for the animation after the data flow example? So how did you do the visualization from Python and pandas to the time series thing you did?
Oh, so that's just JavaScript. That's just it was just raw JavaScript that we kind of put together to demonstrate that.
Okay, and for the prediction, did you use a library like scikit-learn or?
Yes, exactly. That's what we did.
Okay, thank you.
Sure.
Thanks. You get a book. Hello.
I'm actually a novice to BigQuery and machine learning algorithms for predictions. So my question is, once I get my data set migrated into big data and some sort of database there, and I want to start making predictions and figuring out patterns in my data, how do I go about, what machine learning algorithm options are there for me in order to start putting together those patterns and start making my predictions?
I would say start simple. Logistic regression is pretty simple. Linear regression is pretty simple. Random forest, the decision trees are pretty simple.
Are there APIs that integrate those kinds of regression models?
Yeah. So actually, one of the other questioners just asked about scikit-learn. Scikit-learn has packages. You basically you feed your data in, and sort of outcomes a model, and then you feed your new data in, and outcomes predictions. So they make it pretty easy.
Okay, thank you.
And there's a lot of exploration you can do with just SQL. Like I loaded these data sets in BigQuery, so I ran, do, as I was saying earlier, countries with a bigger population are correlated to making more goals. The correlation was 0 until I removed China from the data set, and then I got 0.3 correlation. Then I removed the USA, and the correlation went up to 0.4. And that kind of early exploration that you can get data back in seconds allows you to see where you should look and how you should segment your data. So for example, there is a big correlation there if we only take countries that call football, for example.
But I think it also just shows that if you're going to spend time worrying about, sort of building machine learning models, the thing you really should focus most of your time on, at least at first, is really features and your data. Being able to, to clean your data, like Felipe was saying, and the actual algorithms almost don't matter. At least they matter in the noise, and a couple percentage points here and there. And you can tweak those and tune those once you're happy with the data that you're putting in. But if you don't have good data, if there's not signal in that data, then the best algorithm in the world is not going to be able to predict accurately.
Thank you. You get a book.
Hi. I want to ask you about if there are any books that you recommend about machine learning, and that one besides that one. And also tools, besides the two that were said here at the talk.
So for books for machine learning, there's Russell and Norvig is sort of the standard one that is awesome. Peter Norvig he's a chief of research or something at Google, and he's pretty brilliant, and so I highly recommend that one. Other tools. There's R might be easier to get started with than pandas because it has some better documentation. But I would pick there are some like learning data sets, like ones there was called like Iris Setosa or something. It's about predicting flower genetics. That could be fun to just run through an example and give it a try and find that it's not all that hard.
Thank you.
Sure.
Thank you. Hey, so I have a question about discovery. Like the cool feature of BigQuery, this is a generic question about BigQuery, is you can put data sets in there and make it open to everybody, right? And I know my friend did it and he shared it with me. I mean, he shared the link with me, so I found it. But how do you find because we shouldn't all replicate like New York City data, I have it, he has it. Right? Is there a way to discover other,
I can tell you what I do here. Whenever I find an interesting data set, I can upload it to BigQuery. Once it's in BigQuery, you can set the public bit and you can share it with other people. I have a couple of websites where I like sharing things. So if you go to reddit.com/r/BigQuery, every dataset, every news I learn about these datasets sharing BigQuery, I place it there. So subscribe to that one. And also my friend Ilya Grigorik, also at Google, he has the site bigquery.es, like BigQueries. And there we share a lot of interesting queries that people write. Go there are really a lot of interesting datasets. And my call to action here is, if you have an interesting data set, put it on BigQuery, set it as public, and let anyone else instantly analyze it.
Right, but is there any plan to have a Google way of doing it? Like in Fusion Table, you can just look for public, and you just give a word, and it finds all the public ones. You know what I mean? So because it's
the BigQuery team, we take feature requests and things that users are asking for. We will build. We haven't had, that was something we had thought users would want a lot of is discovery, and then we didn't get a lot of requests for it, so we haven't built it yet. So we have a public issue tracker where you can set feature requests. I would encourage you to request that feature, and then hopefully we can get started on that.
Yes, thanks.
So I'm really new to BigQuery, and I'm also a little bit late to this section, so apologize in advance if you guys already covered this. But you use the example World Cup, and I've seen that in some countries where gambling is legal, there's a lot of websites that will provide tips on which team to bet on. Have you seen any website using BigQuery, then the prediction API to give out tips to people and monetize that type of service? And if so, is that does that match with your ethic, or how do you guys feel about it?
We don't really know what users are using BigQuery for unless they tell us about it. And as far as I know, there's nobody that's doing that. The people use it for financial analysis or even Bitcoin arbitrage, but I don't know I haven't heard about anybody using it for gambling.
Okay.
Yeah. Then again, this is not gambling advice. Please don't use our predictions to gamble.
I don't promote it either, but I'm just wondering.
on the other sense, every time you use data for decision making, you are making a prediction. Every time you make a decision, you are gambling on that happening. So it's not pure gambling, but yes, we are always making decisions and somehow predicting.
How accurate would you say are all those predictions? Like you just show us predictions of like which team is going to win. Like, have you guys done some sort of research on like how many times actually was matched to the team?
They're extremely accurate.
Whoa. Thank you.
I don't actually know. I hope they're very good. I mean, they did pretty well on the training sets or on the test set, the Premier League, but time will tell. We'll see.
Okay. Cool. Thanks.
Sure.
Thank you. Have 30 seconds left, or? I don't know.
Yeah,
That's
my
it.
question was basically already covered, so I'm
Okay.
just here for.
You just want a book?
Yes.
Quick question then. I see you use data flow and
Yes.
Python. So when is it in the pipeline to support Python and data flow? Because all the examples were only showing Java.
That's a good question. I don't know of any plans, but I don't know of any plans not to.
Yeah, the plan with Dataflow is to be language agnostic, but we had to start somewhere. We started with Java.
Thank you.
But that's a good feature request.
Sounds like we're out of time, but I'm happy to stick around. Actually, since Google I/O is over, I'm happy to ask any more questions, or if people want me to sign a book, I'll be happy to sign a book.
It's over. Thank you very much. I'll see you next year or around. Thanks.